Hi, okay, this video is for your module 6. I'm going to finish our module 6 by today in this video. So I hope that I'm going to fasten it so that the video is not going to be so long. And this is for bit parallel adder that you already learned previously, and you also did discuss with your friend on how to create and design and draw the 4-bit parallel adder, isn't it? So it's good for you to have that group because you're going to actively learn by yourself, and it's going to make you remember much more rather than just doing the existing lecture. So in this video I'm going to touch on after your full adder. Basically this one is also in a parallel adder, which is combines of a ripple carry adder and also loop head carry adder, but we're not going to jump too deeper, but you still also can look into your module, only that you can go through what is basically ripple carry adder on the theory part, which is circle simpler than look a head adder, a carry adder, and then about the output and etc. You can go through and read it because this one is more into theory, not included on the designing, drawing, etc. So same also to look ahead carry adder. You can go through it, which is speed up the addition process by eliminating ripple carry adder, and there is also carry generation and carry progression that I'm going to look into it also. So after we finish our half adder, full adder, which is our basic adder, and then we learn on the parallel adder. Now we want to look into the comparator. So comparator is the purpose of comparator is to compare two n-bit binary value to determine which one is large, or in other words, you want to compare two numbers. So it's easy for you, right? It's going to have at least two single bits input, which is x and y, and then the output it's going to have three lines, which is x more than y, x equal to y, and also x less than y. And for XOR gate, it can be used as a basic comparator, while you use XOR to check the single bit inequality. So this is the examples on what this sentence is about, which is on the XOR gate as a 2-bit comparator. You can see that if let's say you have a 0 0 over here using XOR, you will get 0 as the output, and it shows that it is equal. So you check again, 0 1 you get 1, so it's not equal. 1 0 you get 1, it also not equal, of course, and 1 1 is equal, right? So how are you going to conclude? So you're going to conclude that if the output is 0, it's going to be a equal. So you check over here, if it is 0, it's equal. The two digits or 2-byte numbers is equal, while if you have 1, it is not equal for the XOR. This is the scenario for XOR only. And then this one is to check n-bit equality x no. So you combine the result of comparing n single bits comparator. So if let's say you have A and B and the digits is A1 A0 and then B1 B0, so you can see that this is the circuit for a comparator. So you can see that A0 B0 over here, and then this one is A1 B1, this is MSP, and this is LSP, and you will get A equal to B if either high indicated equality. So how are we going to look it? There is an example which is A equal to 1 0 and B equal to 1 1. So from here you can see this is a circuit, and if let's say you are having this one is A0, this one is A1, B0 B1, so we take 0 first. A0 is 0 and B0 is 1. Another one, A1 is 1 and B1 is 1. So what you're going to look into here is you're going to get similar like this, and you're going to get 1 as your output for your, so similar also from here. If you have this XO, the output will be 1. So this is the basic things. Continue. Similar also here, if let's say you are having same value, the output will be a 0. So you convert it, you're going to get 0 1, and this is the AND gate. So you know that in gate you're going to get 1 if let's say both is similar. So you can see your output is 0, means that it is a not equal. Low indicate the not equal. So there another example is design a single comparator for compare x and y. Determine whether x equal to y, or x less than y, or x more than y. So this is the solution. You need to draw the truth table first, and after you get it, using your single comparator, so you will get these kinds of situation. So where is your single comparator? This is your single comparator, which is 2-bit comparator, which is a single comparator. Move. Okay, then what you're going to get if you have equal, you will get x more than y. You can see over here it is 1 because it's equal. If 0 and 1 is not equal, so you're going to put like this. So from this truth table, because this one you're going to play around by yourself, and you will get this kind of truth table, and after that you're going to put the output equation. So from here you will get x, y, y. If okay, this is not this one, so this one is, this is the first output, second output, and then third output. So you need to separate it, the output 1, output 2, and output 3, and then you're going to get this kind of circuit. You can see that you have 3 output. Similar also what you already learned in your module 5. You need to see how many your input, how many your output, right? So you need to have separate circuit, but you know that all the outputs are having the same combinations of input. That's why later on you can also combine together. So this is the answer. You might try by yourself also. Okay, there is also another example. You can screenshot this example and you can try it. So this is the solutions. Quite easy because you can just using the scenario given and you need to draw the true tables. Similar also like this. What you're going to get for your output. So this one is MSI chips 74LS85. This is for 4-bit comparator. So you need to remember this name because normally in your test or your final exam sometimes they are just picking up by using MSI chip 74LS85. So you need to know, oh, this is the 4-bit comparator. So this is how it look like inside these chips. So you already learned how to calculate from 1 until 16 if you have 16 feet of your chips. So you can see that you have 8 input all together because you have basically 2 digits of input with the 4 bits each, and you have 3 outputs. So from here you can see that if let's say you look into first, which is MSB, if let's say A3 and B3 is equal, so you need to compare another one, which is B2 and A2. Is it equal or not? If let's say it's already big, so you can just direct pick this one. If it's equal, so you need to compare another one, B1 with A1. So it's still similar. You need to compare another one, which is E0, B0. And if let's say it's more or equal, you need to stop which operations it's this. So this is the example. Determine the A equal to B, A more than B, or A less than B output for the input numbers shown on the comparator. So you need to see that first of all you check your MSP. First of all it's same. So you need to check another one. This and this one. Oh, it shows that A equal to B. So your output is directly over here without you going to check another one. See, compare A3 and B3, and then if let's say it's similar, you need to compare the A2 and B2 because you see that it's not same, which is A more than B. So stop comparing, and this is your answer. So that's why you're going to get your output as 100 for A more than B, A equal to B you get 0, A less than B you get 0. So high value only for A more than B. There is another example also. This one is for bits. You can try it also. First of all, what you're going to do, you compare their MSB B3 and A3. First it's equal, second B2 and A2 is equal also, B1 and A1 equal also, but for BO, B0 and A0, it shows that A more than B, so you get similar 100. So this is the step. So you can see that this is another examples how you're going to combine it together. If let's say you have one single comparator but you want to combine it together, what had happened after this? Because this one is you are comparing you 8 bits like 8 bits of numbers. So you can see that it need to be connected to the corresponding input of the next stage. So for lowest order comparator, A equal to B must be high, while A is more than B and A less than B must be connected. So this is for cascade connections, how we're going to combine it together. So let's move to our decoders. So for decoders, you can see what is the function to detect the presence of the specific combinations of bits or codes on its input, to indicate the presence of the code by specific output level. So decoder has n input line to handle n bits, and from 1 to 2 to the power of n output line to indicate the presence of one or more n bit combinations. So the output is 1 if its label matches input. So enables input pin, which is EN, is used to enable or disable the decoder output. So this is the pin for the decoder to enable or disable decoder output non input. So you need to know the theory or the details of the decoder, including the EN, and then the output is 1 if the label matches input. So type of decoder, there are several. One is binary decoder, second is BCD to decimal decoder, and third is BCD to 7 segment. In binary decoder, you have 3-byte decoder and also 4-byte decoder, which is one from to 8, which is 8-bit, 1 to 16 for 4-bit. So still on the decoder, you can see that it is for a binary decoder that recognize a binary patterns of its input and active the output whenever that pattern occur. So you're going to use N if you want the output to be high, and you're going to use NAND if you want the output to be low. So this is the example of decoder that produce high if, let's say, you have 1001. This is the base 2 binary occur at the input. So this is the example of your decoder, what you're going to get afterwards. So this is the examples. You need to develop the logic required to detect the binary code 10010 and produce an active low output. So you need to check what the details on low and etc. So there is already keywords here, and that's why after that you're going to use your NAND gate. Another example is when the output is active high for each of the decoding gates. In the picture, what is binary code appear on the inputs? The MSB is A3. So there is a solution. You might try it. Just give and show you the answer. And in this slide, you're going to look into 3-bit decoder. As you know that there is 2 types of decoder, 3 bits and 4 bits, that we're going to touch in our model 6. But sometimes it is good to have a general purpose decoder that can decode all the possibility of binary pattern at the input. just as decoder has multiple output, but its output will only be active if you have a unique binary pattern exists at the input. So this is the example of truth table for 3 bits decoder. So basically you can try to look it and compare it together, and you're going to get the output one like this, and that's why you get the function of SOP, and you're going to convert it into your digital circuit. N is used because we want an active high-low. Check back the previous notes that is inform you what gates you're going to use if you want active high or active low. So this is a symbol for your decoder. You have 3 variables of input, and you have this for your output. For example, if the input of 101, you're going to get the output Q5 equal to 1 only. So notice that only one output will active with a unique binary pattern at the input. So this another one is under decoder, still decoder, but it is 4-bit decoder. So you can see decoder can be called n to the power of n, or 1 of to the power of n for the same decoder. So the common MSI decoder chips is 2 to 4, 3 to 8, and 4 to 16. So what is this? Is like this. You have 3 for input, and this is for your output, 3 to 8. If let's say you have 4, you're going to add is 4 equal to 16. So 74HC154 is one of 16 decoder. Please try to remember the name of the chips. And then it has 4 active high input and 16 active low output. It also has 2 active low enables EN pin, so you can see over here, and this pin is used to select the input, the IC. If we use more than one chips, to use the IC, these 2 pins must be connected to the low. And this is the real picture of the 74LS154. And also it's provided the truth table. You can see it's quite long and big because you have 4 input. So you can try this also at your home. And yeah, through here, if let's say you have the input, and also you can see the output too. Address decoder. Decoder is used a lot to decode an address of a computer. This is on your computer system, so you need to know what happened in your computer also, rather than you cannot open it. And yeah, rather than if let's say you can open your computer, what happens, you need to know every detail inside. Similar also on decoder. Decoder is used a lot of decode and address of the computer, so you can go through and read all the details about your decoder. And you can see this is the examples of your address decoder. You can see that you have a port address 0100, and then IO request, which is low. This is your RO request ON EN enables. This is for what? To enable your output, isn't it? So you check back your previous slide. There is information out regarding that. A simpler computer I/O part system with a port address decoder with only 4 address lines shown. This is the example. And still under your decoder, I think it is until that only. You can try the example and look what happened. And we're going to do, before we going deeper on our BCD, still under decoder, but there is another one which is under BCD to decimals. You can see that your BCD basically is binary coded decimals. BCD is a way to express each of the decimal digits with the binary code. So they are only 10 groups code for the BCD system. So this is the code from 0 to 9. You can see that you have 10 code groups in the BCD system. So this is the example. I think it's quite similar also with your numbering system, so no need to worry much. Only you need to remember BCD decimals, what type of your chips and what happened inside. And this is the truth tables. You need to understand all for your truth tables and frequently referred as one of 10 decoder. The same as binary decoder, expect only 10 decoding gates required, so it's quite many. And not going to touch deeper. So this is BCD to 7 segments. You normally use it in your calculator. So this is how it's look like. Sometimes also there is a watch that using the segment display, 7 segment display, right? So you can try go through and read it all the detail. And this is the output truth table. You can see what you're going to get for the display. It's quite cute. After that, after this, you're going to learn it and try. Maybe you can try it using your own groups or by yourself. You try to get the display for your own calculator. So this is how 1 2 3 4 0. So you need to label all A, B, C, D, E, F, G. Later on, you're going to play around with the LED light over there. If let's say you are in the lab, normally you can see it, but because you are currently doing online, so you can try using the simulator. So now we move to new subtopic, which is encoder. So encoder does the opposite. Of course, you know decoder, encoder is totally different together. So you can see that it is a for convert decimal to BCD. A binary encoder encode information's data from 2 n input into n bits code output. So you can see that if you have 2 n input, so your output we have that n bits code. So this is to the power of n input, and this is your n input. So it's vice versa from the decoder. If let's say in your encoder you have it for your input, and for your output you have 3, something like that. While for your decoder you have vice versa, which is 3 over here for your input, and for your output you're going to have 8 output, right? Normally something like that. So encoder reduce number of bit needs to represent given informations. So there is two type of encoder, which is decimal to BCD encoder and parity encoder. So this is encoder for decimal to BCD, which is 10 input decimals, and for output BCD, also called as 10 line to 4 line encoder. So it's quite huge. You have 10 input over here altogether, and you have 4 output. So this is the decimal input and BCD output. So your output will be in your code BCD. So please remember that it is not a binary form, but it is a code BCD. So this is the truth table, which is vice versa with your encoder. So this one is pengcode, and or also it's called as encoder. So pengcode is in Malay and encoder is English. So logic symbols for decimals to BCD encoder. This is the logic symbol. So please try to remember it, how it look like. And from two table you can see that you have several high, which is 1 3 5 7 9, and etc. You can try it and look it, and that's why after that you can directly convert it to your logic circuit. So this one is another example. You can try it. I show you the solutions. And this one is under parity encoder, which is using IC74HC147. So and then after that it's perform the same encoding functions, but with the additional features. You can see there is slightly difference, and then you produce the BCD output corresponding to the high decimal value. Add the input and ignore the lower value. So you can see that there is an example. You can go through it. If P9 and 5 low at the same time, only P9 will be recognized because it is a higher priority. So this is what a higher priority, which is you're going to only recognize the higher pin numbers. So the output will be 011049 because of active low at the output. So that's only on our parity encoder. Now I'm going to touch on our next subtitle, which is multiplexer or multiplex. You have demultiplexer. You have mux and demux, of course. For mux, you have a multiplexer. Mux is a device that allows digital information from several sources to be routed onto a single line for transmissions over the line to command destination to a common destination. Okay, so the basic multiplexer has several data input line and single output line only. So you know that mux, if you have mux, you need to know it is a many to one. So this is the equation for select line control, which input route to the output route. So you need to know number of select bits, which is log number of input, and also divided it into log 2. So mux are also known as a data selector, and the mux known as a data distributor. This one is the example, which is under data selections. This is your input, and this is the output, one output only, because you have a multiple input, but the output side you're going to have only one. Please remember that, so you can easily draw your marks. So this is example, marks 1 of 2. You have when s equals 0, y equals to d, and when s equals to 1, y equal to d. So this is a true table. I think it's 0. A more compact form can be produced. So this is the design truth tables, and then you also have the circuits. This one is your Boolean circuit equations. So there is also another example. This one is 1 of 4, rather than this one is 1 over of 2. Now you have many input, but your output will be only one, isn't it? So there is also another example. Please try it and understand it. This one is under your timing diagram. It's quite similar. You can convert it into your truth table to get full understand on what happened to your timing diagram. Several exercise I just show you. And now we look into our D-marks or demultiplexer, which is a D-marks is basically reverse. Of course, same also what happens we learned previously, decoder, encoder. It is vice versa, and it takes digital information from one line, distributes given numbers of output line. So the reason is D-marks is known as a data distributor. That's why you have one only for the input and you distribute it to many. That's why you have many output. You have only one input. This is the keywords. For D-marks, you have only one output, but for D-marks, you have only one input, but for marks, you have only one for the output. So this is a truth table. So the below part is the compact version. You can try to look it and compare it what in your truth tables. So this is the example of the data input line goes to all the AND gate. So two data select line enables only one gate at a one time. So please make sure you remember that. And I'm going to go to the last, which is code converter and also parity generator or checkers. So the purpose of code converter circuit is to convert from one type code to another type. So it depends. So the example is 3 to 8 decoder. Convert binary number to one hot coding at the output. And another one is vice versa, of course, 8 to 3 encoder encoder perform the opposites, which is vice versa, of course. Many different type of code convert circuit can be constructed. So the common examples are BCD to 7 segment decoder, as explained the decoder sections. So error can occur as digital code are being transferred, of course. You're going to know about this. Sometimes also having an error, and the error tag form the undesired changes in the bits that make up the code information. That is one change to 0 or 0 to 1. So you can change. When an error occurs undetected, it can cause serious problem in your digital system. So this is the basic parity logic. to determine whether number of ones or zero, odd or even. And this is the informations of the parity checker and also parity generator. Please remember also the number of the chips for each uh, chips for all what you have learned on the circuits provided, whether it is a comparator, whether it is a encoder or decoders, the points, and you can just go through what's the theory for parity checker and also parity generator. So that's all for your module 6 altogether on one more video. So later we're going to discuss this on our class. I hope that you have a basic understandings on that, and you can check also while you are watching this video. You can also check your modules, which is your books or your ebooks. Thank you for your watching and have a good day. Bye bye.